Great. Thanks, Chester, for the introduction, and also thanks again for reminding me to talk at the SFP Analytics meetup, and also thanks Bill for hosting and organizing this event. And hello to everyone attending this meetup. So today I'm going to talk about the work we did recently at LinkedIn, and for our Spark infrastructure, and which is the push-based shuffle service for large-scale data processing, and which we name Magnet. So before we get to there, probably just a bit more context on why we're actually working on this. So if you look at the trend of the recent improvements in Spark, or pretty much like more of the similar massive scale query processing engines, so we can actually see a very sort of a condensed batch of optimizations that's happening around how those engines are leveraging the CPU compute resources. Right. So just from the Spark perspective, in the past, probably 2 to 3 years, we have seen quite a few work in this area, right? Starting from the cost-based optimization, to the adaptive query execution, which is like one of the most highlighted features in Spark 3.0. And there's also the vectorized execution engine, and even native execution engines, right? So if you attended Databricks, talking about their, Fulton execution engines, you are probably also familiar with those terms. Right, so a lot of those CPU optimization techniques, they are pretty, important, just to making sure that, these large-scale query processing engines can actually scale, and it can actually become more and more efficient in processing those workloads. However, one more thing that we're actually noticing that is not being worked on so, aggressively, recently is optimizations on the I/O front. And we actually have seen, very few optimizations, targeting, improving the overall I/O for large-scale deployment of massive-scale query processing engines. And among the I/O, we also noticed that Shuffle is perhaps the heaviest I/O operation, and especially for a DAG, execution engine, where the data do not rely on, external storage such as an HDFS or S3, for storing the intermediate data. The data is just basically going through the DAG execution engine through Shuffle, right? And for some of the larger scale deployments of Spark, such as Facebook and Uber and Netflix and maybe even us. Like this is probably from some of our past conversations in the community meeting discussions. But we have started to identify that the Shuffle operation is actually becoming another scaling and performance bottleneck. And so, to get there, I think first I want to just provide a very quick, introduction for the Shuffle itself, right? And as many of you probably already know, the Shuffle process is actually a pretty vital piece, in the MapReduce compute paradigm. It powers, the Spark, compute engine, as well as many other modern compute engines. Right, so the sole responsibility of the Shuffle process is basically to transfer the intermediate data across stages, with a mesh connection between the mappers and the users, right? And so in a typical deployment, and such as the one we have, on top of LinkedIn Spark infrastructure, we're actually deploying Spark on top of Yarn, and in such a typical deployment scenario. For each of the compute node in our clusters, we'll actually be deploying one Spark external Shuffle service, right? And when the mappers, inside the Spark executors are running, and they will start, generating the Shuffle files. And the way they're generating the Shuffle files are termed as the sort-based Shuffle. Basically, the mappers will need to actually sort, all the Shuffle data based on, the partition keys or the hash value of the partition keys. Right, so that will basically end up into such a Shuffle file for each of the mappers outputs. In each of those Shuffle files, you will basically have individual Shuffle blocks concatenated together, where each individual Shuffle block represents the records for that particular Shuffle partition, right? And all those data are actually stored locally and served via the Spark external Shuffle service that is also located on that same host. And when the next stage, the Shuffle reduce stage starts running, and all the reducers, starts launching, right? So the reducers will actually start fetching all those individual Shuffle blocks, from the remote Shuffle services. And each reducer is actually responsible for processing, one Shuffle partition, right? So they will basically talk to the shuffle services, hosting the, shuffle blocks, of the corresponding partition, and then fetch, all the unique blocks, to get their task input data, right? So as you can see, right, so because of every single mapper is going to produce, the shuffle block for every single shuffle partition, right? So the reducers, each one of the reducers needs to basically fetch, the shuffle blocks from all the mappers, in order to get the entirety of its, input data, right? So this kind of shuffle operation is becoming a scaling and performance bottleneck, especially at large scale deployments. And to talk about the large scale deployments, it's probably worth also mentioning about the current scale of things for the Spark infrastructure at LinkedIn. So right now across our two business production production clusters, we have more than 11,000 nodes, compute nodes, and they actually represent a pretty large amount of compute resources, right? And on top of this cluster, every day, we run like more than 30,000 daily Spark applications. And all those Spark applications together, they pretty much contribute to more than 70% of the cluster's total compute resource consumptions. And in addition to that, they will also be shuffling like more than 10 petabytes of data every day. And our infrastructure is also growing pretty rapidly. We have actually seen an average of a 3x growth year over year in the past 2 to 3 years period time frame. Right. So, when you're starting operating things at this kind of scale, and especially for Shuffle, right? So we actually started seeing multiple issues, with Shuffle. So the first issue we actually see is the reliability issue with Shuffle. And, especially when the Shuffle service are under heavy load, say for instance, during the cluster peak hours. And, we're actually starting to see some Shuffle service availability issues. Right, so this is actually a graph that that's from our dashboards, basically showing, the different type of shuffle-related failures that we have been seeing on our clusters on a daily basis. It's just from one of our clusters, right? So if we nail down to one particular type of exceptions, and we can actually see that, sort of by the end of last year, we're actually sort of averaging around, sort of a couple hundreds, and sometimes even more than 1,000. In extreme cases, even more than 5,000, shuffle stage failures. And all these type of failures are really all due to, the shuffle service, availability issue when it's actually under heavy. And another category of issue we have seen is the efficiency issue with Shuffle, right? And, at LinkedIn, as well as many other sort of similar large scale deployments for Spark. And we're still storing the Shuffle data, on top of the sort of hard disk drives, right? So when we're storing the Shuffle intermediate data on the hard disk drives, and that also combined with the average size of the Shuffle blocks being pretty small, we actually have done an analysis, right? So which reveals that the medium size of the Shuffle blocks in our clusters is only around 7 kilobytes. Right, so you can sort of imagine that when you are having such large amount of sort of Shuffle block fetch requests served through Shuffle services on top of the hard disk drives, that can actually create a pretty severe sort of efficiency issue, hurting the disk overall throughput. Right, so this actually creates a a relatively long Shuffle wait time, and you can see from this dashboard that I took a screenshot. Right, so across the two of our business production clusters, the total amount of time spent waiting for Shuffle data to arrive is actually in average, occupying like somewhere close to 15 or even 17, and sometimes even more than 20% of the entire sort of task runtime. So basically, you can sort of imagine that around 20% of the cluster compute resources is basically sitting there idle, waiting for those remote Shuffle service to arrive, right? So when you're operating things at extreme large scale, this can be a pretty significant waste, right? And the last, but not the least issue we're also seeing is a scalability issue, right? So the scalability issue is more, sort of arising during the cluster peak hours, right? Where it basically reflects itself as the job runtime inconsistency. And because in our clusters, there's many production, sort of workloads that is kind of expecting some kind of SLA for how fast, their job's going to compete, right? But, when we actually go into the cluster peak hours and due to Shuffle, we can actually see that, all of a sudden, the runtime of the particular job can vary a lot. And so this is also a screenshot that we're actually taking, for one of our production jobs. And we're basically just trying to, sort of, attribute, all the sort of, task runtime, based on different categories, right? Such as CPU time, GC time, like, task runtime, network IO time, and the shuffle read time, right? So you can see that, when the shuffle, sort of, read time is peaking, there's multiple peaks, including this one, which is a pretty big peak, right? It's just going to cause like, sort of a very uncontrollable, like, sort of job runtimes for these production jobs. And especially during the cluster peak hours, when the shuffle services are under heavy stress, under heavy pressure, right? It further sort of, magnifies, this kind of effects, leading to, many production jobs necessarily not unable to be met, right? So this kind of combination of the, reliability issue, efficiency issue, and also this scalability issue is basically what we have experienced, sort of this operating shuffle at large scale, right? To be able to actually tackle this kind of problems, to be able to make sure that, we're able to provide infrastructure, that can not only be efficient, cost effective, but also be, very predictive, to our, sort of the users in terms of what kind of SRA they can expect. We come up with the Magnet Shuffle service project. So in this, sort of a project, what we effectively did is we come up with a novel push-based shuffle mechanism. So the work itself, was recently published as a industry track paper in the RDB 2020 conference. So for people after this particular talk, if you're interested in knowing more about what we did with this work, you can actually, go search for this paper. I'll also probably provide, some information in the end for how to access this paper. But for now, just going to give some kind of a high level, overall sort of highlights of the solution, right? So with Magnet Shuffle services, we're effectively trying to achieve three things. We're trying to, basically, have a better sort of, overall IO efficiency in our cluster by converting the small random reads in shuffle to large sequential reads. As part of this process, we're also going to, actually introduce a second replica for the shuffle intermediate data. And this process also helps to improve the overall reliability, for shuffle and Spark. And in addition to this, we're also incorporating locality-aware scheduling of the reducer tasks, which can help to further improve the performance and, of the shuffle infrastructures. And in addition, we're also, contributing this work right now, to the open source Spark community in the Spark 30602 Apache GR ticket. Once again, we've also come to, like, the details of how to get to those, sort of external information, the paper, and also the SPIP ticket towards the end of this, talk. But for now, I probably want to first present, like, the results we have seen so far with Magnet Shuffle service, to convince you guys, this is actually work, worth paying attention to. So we actually have been, sort of benchmark, the Magnet Shuffle services in multiple ways. We started with, a TPCH benchmark, just to show, how Magnet Shuffle services performs, with typical SQL style, compute workloads. And we're using 1 terabyte, TPCH benchmark, to do this benchmark. And we actually see pretty good results, right? So in this table, we're actually listing the percentage improvements, with Magnet across those 2 dimensions. The shuffle fetch wait time, which was the time I showed earlier, right? That actually occupied close to 20%, of the, cluster compute, resources. And also the overall executor task runtime, which can relatively translate to, the jobs into runtime. Right, so with Magnet, we're actually seeing a pretty significant reduction, in the shuffle fetch wait time in general, right? So for some of those queries, we're seeing almost very close to 100% reduction, which means it's almost eliminating, all the time it was previously waiting for, the remote shuffle data. And also in many cases, we're seeing, reductions, around 90%, which is still very significant. Right, and based on how sort of large, the shuffle plays a role in these individual queries, some of those queries might be shuffling more data, and some of those queries might be shuffling relatively small amount of data, right? So we can actually see that, the impact, to the executor runtime, in certain cases can also be pretty significant, right? So say for instance, in query 5 and query 8, where the query is shuffling relatively larger amount of data, we're actually seeing like more than 30% reduction, in the executor total task runtime. In addition to the TPC-H benchmark, right, so which probably does not very reflect the production workloads we have in our production clusters, we also benchmark with our sort of production workloads at LinkedIn. And in this case, we're actually benchmarking with a machine learning model feature generation job, which consists of tens of shuffles, and which shuffles in total close to 2 terabytes of data, right? And in this job and with Magnet Shuffle service, we're also seeing a very significant reduction across these 3 dimensions: shuffle fetch wait time, executor task total runtime, as well as the end-to-end runtime, job runtime, right? So we're pretty much seeing like close to 98% reduction in the shuffle fetch wait time. And all the reduction is directly translating into the executor task runtime, leading to like more than 40% reduction of the total compute resource consumption for this particular job. And in the end, this also provides more than a quarter saving of the job's end-to-end runtime. So this is actually pretty significant, right? And one more thing I want to bring up here is Magnet, it also assumes very little of the job itself, right? So it doesn't matter whether it's a SQL, sort of style compute, like in the TPC-H benchmark, or it's maybe a little bit combination of SQL and non-SQL compute, such as in this case, this machine learning model feature generation job, right? As far as it's doing shuffle, Magnet can actually provide benefits to those jobs. And at LinkedIn, we're also already in the process of productionizing Magnet Shuffle services. We have already onboarded multiple production flows, that are shuffle heavy. And throughout all those production workloads, we have also seen very similar reductions in the shuffle fetch wait time, task runtime, as well as the job's end-to-end runtime, right? And more importantly, in addition to just bring this reduction to the overall runtime, we're also bringing one more benefit, which is the job's runtime becomes much more stable, even during the cluster peak hours, right? So this can also help to provide a better guarantee for the SLAs for those production jobs. And as we also anticipate that as we onboard even more production workloads, the Magnet effect, which is all the benefits Magnet Shuffle service is able to provide to our infrastructure, can become even stronger. This is because we're also going to convert even more shuffle workloads into this optimized shuffle, optimized paths, which can further reduce the pressure on the shuffle services. Right. So now I have talk about the results we have seen with Magnet Shuffle services. So in the second half of this talk, I'm actually going to go a little bit deeper into what we actually did behind the scene for the Magnet Shuffle services, and what are the various sort of innovations we're actually bringing to this picture to help Magnet Shuffle services achieving these kind of results. I think in the core of the Magnet Shuffle service is the concept of this push-based shuffle. So I think many of you probably are already familiar with the pull-based shuffle, which is the shuffle mechanism I described in the beginning of this talk, right? Where the mappers will basically going to generate the shuffle files locally, and the reducers from the remote executors are going to basically fetch those individual shuffle blocks through the shuffle services, external shuffle services, across all those mappers, right? And we have already seen, the various issues with that kind of approach, right? So with push-based shuffle, what we're trying to do is we're actually trying to introduce push-based shuffle, in a best effort manner. And also we're not aiming to, use push-based shuffle to entirely replace the existing shuffle mechanism. We're rather designing it as a complement, to complement, the existing shuffle. So, with push-based shuffle, after the mappers finish generating the local shuffle files, they also took this additional responsibility, of dividing the local shuffle files, into multiple groups, and each group will basically include, a various number of, sort of continuous shuffle blocks, in the shuffle file. Right, and as these shuffle files are actually being divided into multiple groups, and it's the mappers will also trigger kick off this process to basically transfer these groups of shuffle blocks to remote shuffle services, and that's why it's termed as push-based shuffle. We're basically before the reducers are running, we're sort of optimistically trying to push those shuffle blocks to reduce shuffle services, remote shuffle services, in order to merge them per shuffle partition, right? So you can see that in this particular process, each individual group of shuffle blocks from the executors will actually be first loaded into memory, and the individual shuffle blocks inside these groups will then be further pushed to remote shuffle services in order to be merged per shuffle partition, right? And after this process is done, we basically have a almost like a second replica of the shuffle intermediate data, right? In addition to the original shuffle files the mappers are creating, with this push process, we're also creating a second replica of the shuffle data, which represents the shuffle intermediate data from a reducer-centric sort of view, where each file represents an entire shuffle partition, right? And when the reducer tasks are actually running, right, and in addition to just instead of just fetching those original shuffle blocks, from the shuffle file created by the mappers, now the reducers actually have this option of fetching its input data from the mix of both the merged shuffle file, as well as the unmerged original shuffle files, right? So all the metadata for where the merged shuffle file is located, how large those merged shuffle file is, and which blocks are actually going to be merged in each one of those merged shuffle files, is actually tracked by the Spark drivers, right? So the driver will basically build a complete picture of for each individual reducer task, how can it sort of get its shuffle input data with the most optimized fashion, right? So we're taking as much as possible from the benefits of those merged shuffle files. And if there's any hole in this merged shuffle file, meaning any blocks might not be fully merged into this block, because we're actually taking a best effort manner, right? So reducers can still fetch those blocks from the original shuffle file, to basically making sure they can actually get a complete input data, for their tasks, right? And here is a architectural overview of the lifespan of how a shuffle works, with push-based shuffle, with magnet shuffle service, right? And in this sort of a lifespan, we can see that when the Spark driver is actually starting the mapper task, and also when the mapper tasks are generating those shuffle files, this entire process is no different, from the existing mechanism in Spark. So the differences happens, when the mappers start dividing those shuffle files into continuous groups and then kicking off this push process. So one more thing I want to mention is, this push process, for pushing the local shuffle blocks, to remote shuffle services to be merged per shuffle partition. It happens in parallel to the mapper tasks. The mapper task can actually finish, the task processing itself and reporting the map status back to the Spark drivers without having to wait for all its shuffle data being pushed to remote shuffle services. This entire push process happens in parallel as those mapper tasks are running, right? So this guarantees that we can achieve a better parallelism for the CPU intensive task processings as well as the IO intensive shuffle data transfer, right? And when the Spark driver receives all the map status from all the mappers for that particular shuffle map stage, right? So that basically notifies the Spark driver that at this point we have already finished all the mapper tasks. And but at that time, there's no guarantee that all the blocks are already merged into those merged shuffle files, right? And also the Spark driver do not have the metadata, for all those merged shuffle partitions. So here we're actually introducing, one more step, between the Spark driver decides to transition into the shuffle reduce stage, such that the driver is actually going to coordinate this process, where it notifies, all the shuffle services for this particular shuffle to finalize and stop, receiving the blocks for merging, right? And as part of this request, the individual shuffle services will also going to respond, the metadata for all those merged shuffle files back to the Spark driver. So with this process, the Spark driver can actually now build, this, sort of a complete picture of for a given shuffle, where the data is actually located and how large this data is. from this sort of a metadata array that is actually trapped inside the Spark driver. So one more thing I want to mention is this array is something that's already existing in Spark, but that existing metadata is basically a mapper-oriented view of the shuffle metadata. We're basically extending this view by introducing this reducer-oriented view, where we can also representing the metadata for those individual merge shuffle files in there, right? And after this process, the Spark driver now can start the reducer stage. It will basically launch all those reducer tasks. And reducer tasks will then query the Spark driver for getting their sort of shuffle input data. And the driver now can actually make this holistic decision, right? So we can see that those reducer tasks can actually get majority of its shuffle input data from those merge shuffle files, but there's a few missing blocks, and it can actually get that from the original shuffle files. And one more thing the Spark driver takes into consideration is it tries to schedule the reducers, co-locating them with the merge shuffle file, right? Because with push-based shuffle, we're actually going to combine and merge the majority of a shuffle partition, for a given reducer task at a single location, right? So this is different from the original shuffle mechanism, where a reducer task input is scattered across, the entire cluster, right? So with this consolidation, that also creates a natural locality preference for running those reducer tasks. The driver will also take that into consideration, to make sure, when we're launching reducers, we try, the best to co-locate that, with the merge shuffle files. So in this way, the reducers can even bypass the shuffle service and can read, locally for getting its, input data. Right. So this basically is like a architectural overview and the process of the push-based shuffle and what we're actually doing, sort of behind it. So now I actually also want to just bring out a few highlights for the Magnet designs, and those highlights are what's actually helping the Magnet shuffle service to achieve the performance results that we saw earlier. Right. So as mentioned earlier, right. So by doing this sort of shuffle block push and merge process, we actually help to improve the disk I/O efficiency a lot, because we're actually converting the small random reads in shuffle to large sequential reads by making sure that we're each time the the shuffle data is actually read from disks, we're not bound by the individual size of the shuffle blocks, but we're able to batch them together into a much larger amount of data for individual reads. And in addition to the disk I/O efficiency, it also helps a lot in terms of cutting down the number of RPCs needed during shuffle, right? So this cut down is achieved in two ways. So one is once we're merging the shuffle blocks per individual shuffle partitions, fetching the reducer task fetching task input data from a merge shuffle file that requires a much less number of RPCs compared to fetching the original blocks, because with the original blocks, you basically need to fetch as many as the number of mappers. But with the merge shuffle blocks, for you're probably only going to need just a few tens of RPCs, to fetch all the task input data, right? So that can be orders of magnitude, sort of cut down for number of RPCs. And in addition, the locality aware scheduling, helps to further co-locate the reducer tasks with the merge shuffle partitions. So this also helps to convert the remote fetch into local reads, right? So which further helps to cut down the number of RPCs. So as the number of RPCs are cut down, this really lowers the pressure the external shuffle services are receiving in our clusters, right? So which is one of the the bigger contributor for like the more stable runtime even during the cluster peak hours. Right. So another improvements or highlights with the push-based shuffle is how it is able to improve the shuffle data reliability. Right. So the reliability improvements is also done in two ways. Right. So previously with the existing shuffle mechanism, the shuffle fetch process needs to be a perfect process. Right. So every single reducer needs to be able to fetch every single block that it needs in order for that entire shuffle to be successful, right? If any block is unable to be fetched, that shuffle failed, and we're going to trigger stage retries, right? To basically rerun some of the upstream tasks to regenerate those shuffle blocks, and then the reducers that was previously failing will then rerun and then be able to fetch those shuffle data again, right? So that's the existing sort of fault tolerance mechanisms, in Spark for how it handles shuffle, right? So with push-based shuffle, so the first part is, this push process itself is actually a best effort approach. So which means if we have any failure during the block push and merge process, it does not impact the shuffle itself. Even if we have failures, during this process, the shuffle can still continue. It's not going to trigger any shuffle failures. And in addition, right, so as mentioned earlier, right, so as we're actually doing this push and merge process, for all those shuffle blocks, it actually creates a second replica. Although this is not a perfect replica, because with the best effort manner, right, so some of the blocks might not be merged, so which means the second replica might only include, say for instance, 90 or even 90% of the data, but still we have a second replica, for that shuffle intermediate data. Right. So then when the reducers are actually running, they will only experience a shuffle fetch failure only if it is unable to fetch a shuffle block both from the merged shuffle file as well as from the unmerged original shuffle file, right? So in our design, in our implementation, if the reducer is trying to fetch the shuffle block from the merged shuffle file and somehow failed due to either disk or network issues, the reducer is able to fall back to fetching the corresponding blocks from the original shuffle files, right? So this way, the second replica of the shuffle data helps to further improve the reliability of the shuffle, right? By making sure that we're less likely to have to rerun stages and regenerate the shuffle data. And the next highlights part is how Magnet is able to handle the stragglers during the block push and merge process. Right. So one benefit of the existing shuffle mechanism is if there's any straggler in the reducer for fetching the shuffle blocks, such as this particular task illustrated in this upper portion of this graph. Right. So here each line represents a task, and how long the line is represents how long the task itself actually ran. Right. And if we have a relatively long running reducer task, it's somewhat hidden by the other tasks, because the other tasks will still be able to proceed, and so the overall effect of this straggler might be somewhat minimal, to the job's overall end-to-end runtime, right? So, but when we're actually switching to the push-based shuffle, right, and if there's any potential straggler, during the push process, that might actually be causing a bigger sort of impact, right? Because if the Spark driver is basically just waiting for all the push process to finish before it starts running those reducer tasks, we can start saying that if there's any struggle in this push process, it immediately start introducing this gap between the shuffle map and shuffle reducer stage, adding this sort of a gap in between where no task is running and where the entire cluster is just idling there and waiting for this push process to finish. Right, so which means a straggler, in the push style shuffle can introduce bigger harm, compared to a straggler in the, the pull style shuffle, right? And we're actually sort of able to mitigate, such stragglers, by introducing early termination, right? So that the Spark driver is able to actually bound the total amount of time and it is wait for the push process to finish before it starts the reducer stage, right? And because of the best effort nature of our approach, we can guarantee that all the reducer tasks can still fetch their data by fetching this combination of both merged and unmerged shuffle files. And then we're also ensuring that the benefits we get with push-based shuffle does not introduce a potentially harmful side effects by introducing this early termination, right? So the last highlights I want to point out is how our approach natively integrates with Spark. So this is actually also important, all right? So there's a couple benefits we can get with such a native integration. So on one side, for Magnet shuffle services to work, it has no external dependencies for other systems. So this is different from some of the similar approaches that you might have been seeing, sort of recently. So I think, Facebook's, they introduced their sort of Costco shuffle service. and which is actually relying on their internal disaggregated storage clusters, for storing the shuffle data. And I think for Uber, they probably also sort of introduced their Zeus Shuffle service in this year's Spark Summit. But I remember from that presentation, they also mentioned that they're probably going to need zookeepers, for sort of orchestrating their shuffle service agents, right? And so having no external dependencies, for other systems, brings big benefits, such as it really simplifies the deployment, the monitoring, and also the productionization for the Magnet Shuffle services. And another benefits is how the native integration with Spark can help Magnet to work with some of the existing Spark features, such as adaptive query execution. So here I'm highlighting adaptive query execution because the AQE feature is also one that requires special handling in Shuffle, and especially for how it handles the join skills. So if some of you who attended the Spark Summit earlier this year, you probably know that one of the the promises by the adaptive query execution feature in Spark 3.0 is how it can automatically handles the join skills, right? And in order to be able to handle such a join skill, right? So it actually requires the capability of dividing a skilled shuffle partition among multiple reducer tasks. And this division is done by each individual reducers only fetch the shuffle blocks from a sub-range of the mapper outputs, right? So say for instance, this shuffle includes sort of 1,000 mapper tasks. And but we identify a skilled shuffle partition in there, right? So to basically spread this skilled partition onto multiple tasks. So what the Spark is doing right now is it can potentially spawn 5 tasks, reducer tasks, where each one of those 5 reducer tasks is only fetching shuffle blocks from 200 mapper tasks. So reducer task 1 will basically say that my task input is from mapper 0 to mapper 199, and so on and so forth, right? So that's how the AQE is able to handle join skills, right? So Magnet, it actually maintains both the original shuffle file as well as the merge shuffle file, right? So in addition to the benefits we mentioned earlier, right, it also enables this native integration with AQE for how it can actually delegate to AQE to handle join skills, especially those skill shuffle partitions. So for all those skill shuffle partitions, Magnet Shuffle service can basically delegate to AQE so that AQE can still use the original shuffle file, for dividing them, across multiple reducer tasks for handling the skills. And for all the non-skilled shuffle partitions, Magnet Shuffle service can take over to make sure the reducer tasks are actually going to start fetching, the much more optimized, merge shuffle file. And so I think these are some of the highlights, I want to bring up here. And so now looking at some of the future works, that we still have, for Magnet Shuffle service. Process for rolling out Magnet Shuffle services to all the Spark workloads at LinkedIn. We have already onboarded, quite some production workloads, but we're still not there yet in terms of Magnet being serving 100% of the Shuffle workloads. And in addition, we're also looking at how we can actually support the deployment in such a computer storage disaggregate setups. So this might be very common in a sort of cloud-based deployments of sort of Spark clusters, where people might be deploying separate compute and storage clusters for dealing with different needs on the compute and storage side, right? And if the Shuffle storage is actually going to be stored in a disaggregate remote storage cluster, and how we can actually incorporate that. Right now, we're actually looking into another separate Spark upstream feature for disaggregated Shuffle storage. And we're trying to see how we can actually combine these two things together to enable that. And we're also right now in the process of contributing Magnet back to the open source Spark community, in the Spark 30602 ticket. And we encourage you guys, if you're interested, to also take a look at the relevant documentations we put in there, and potentially discuss and even potentially contribute to this feature. And last but not least, we're also sort of thinking about sort of exploring the applicability of the push-based shuffle to streaming processing engines. I think for the streaming processing engines, it has some unique requirements which right now is not really being covered, because we're still thinking much from a a batch processing, perspective. And this might be, another areas where we can, sort of, making even more contributions, to the community. And so this basically concludes, the materials I prepared for this presentation. But before I finish, I actually just want to show a few relevant links, in the upstream Spark ticket that we have created. So this is the SPIP ticket we have put up, for contributing our work to the upstream. And in here, we actually have also linked, our VRDB paper. So if you're interested in reading the paper itself, you can actually find it here. And in addition, in the SPIP doc, which is the doc that we're highlighting, our, sort of design principles, there's already quite some, sort of discussions in the doc itself. But one more thing I want to highlight is, in a separate documentation here, we have also shared, a GitHub branch where we're actually already sharing, our current implementation for Magnet, with the broader community. And so right now, this branch of the code is already being evaluated by a few companies such as Facebook and Databricks. As we're collaborating with them to see how we can push forward on this. But in the meantime, if you see a similar issue in your environment, and also if you feel that you want to try it out, for push-based shuffle, you can also check out this branch. And so right now, this is actually based on top of the Spark master branch. You can take a look at the implementation, or even try to deploy the Magnet Shuffle service in your environment, and provide feedbacks to us. That would be appreciated. And I think this pretty much concludes my talks. So now I'm open up for questions.
Thank you, Ming. And it's open for questions. I mean, before the people sending questions, they've been asking, see whether it's possible to share the links you just showed, and also on the slides you prepared.
Yes, this is possible. So what I'm thinking is I'll probably add one more slides in the slide stack, and
Okay.
just to link to all the links I actually just briefly showed, so that it's easier for people to, look at those different things.
That'd be cool. So if you can share the final slide deck to me, either through whatever the URLs or the deck itself, and I'll share on the meetup page, and so with all the members.
Right.
And for all the members, the recording, this talk is recorded, and the recording will be available later on the YouTube channels. So anybody has a question? I know some people posting questions directly on the chat. Please post it on the Q&A section. So if you have questions.
Is there a, okay, I see there's a separate Q&A, okay.
So one of them posted it on the chat. Let's try to find it. So okay, here's the question. Is your memory copy overhead going up due to the push-based implementation?
That's actually not the case, right? So one thing I didn't go too much into the details in this talk, but it's actually covered pretty much in detail in the paper. So the implementation for Magnet is actually pretty resource light for both CPU and memory, right? So in terms of the memory itself, our implementation pretty much caches nothing on the shuffle service side. I probably I mentioned in the beginning that we're actually going to cache those group of blocks on executor side. But this is only caching the Spark executor side, and we're only caching, like say for instance 2 to 3 megabytes of data at a time. And so the overhead of caching on the executor side is very minimum. If you think about most of the Spark executors have at least a couple gigabytes of memories. Right. On the shuffle service side, we're caching pretty much nothing. Right. So which means even during extremely high sort of concurrent workloads, which in our case we actually have also benchmarked internally to have like sort of thousands of concurrent sort of push or fetch request hitting a given shuffle service at the same time. And even under such extreme high sort of workloads, we still also didn't notice any significant memory consumption increase compared to the existing shuffle service. Yeah. So memory consumption wise, we do not have any concerns there.
Great, thank you. Any other question? I didn't see anybody posting questions on the Q&A session. Any questions? Yeah, here's one question.
Mhm. Oh, yeah, right. So the question is if there's any non-configuration changes required to the Spark jobs to use Magnet. So the thing is, right now to use Magnet, the only thing needed is just a configuration flag, right? So where people just needs to turn a set of flag to true to enable this feature, and there's no change required on the Spark job side. All the existing job can be able to benefit from that. Yeah.
I mean, you mentioned that this feature has been added, giving back to open source. So is the which version that Spark can show up on this feature?
So yeah, so this is another part I want to just sort of further confirm, right? So this is we're still in the process of contributing this to the upstream. So which means that process is working with the community and also working with Databricks. Just making sure that all our patches are actually taking a even closer look by the community members before we merge this into the Spark itself. So that work is still in the process. So according to our earlier discussions with Databricks, we do want to explore the possibility of incorporating a version of the Magnet solution into Spark 3.1. I think Databricks side is probably aiming for a release either later this year or early next year. This is based on their timelines. But from our side, we're just trying to see whether we can actually work with that timeline, to release an initial set of the feature of Magnet into the next release of Spark.
Okay, 3.1, somewhere around that time.
Right, right.
Any other questions?
Sure.
There's one more question from DB. Oh, wow, DB.
Oh, hi, DB. Yeah. Okay, so this is about the the extension to the Kubernetes, right? So I think the reason I mentioned we're exploring the integration with Spark 25299 is probably also related to that, because one of the reasons for Spark 25299 it's basically introducing pluggable API for Spark to write shuffle data to external storage, mediums, is to actually support, Spark on Kubernetes deployment, for storing the shuffle intermediate data, outside of the port, for running the Spark executors. And so I think there's probably two aspects to this. One is being able to support this compute storage disaggregated deployments, right? So Kubernetes is one of such a deployment, right? So where your executor port probably do not have the storage medium for storing the shuffling intermediate data, and we're actually actively looking to how we can incorporate Spark 25299. We're also discussing with folks behind that SPIP, to just discuss how we can actually align those two work. But I think in addition to this, there's also another part, which is how can we support the Magnet Shuffle service on top of Kubernetes. Because right now, our implementation for Magnet is only for the Yarn deployment. We're actually also leveraging some of the existing Spark on Yarn support or features to actually make Magnet working on top of Spark. And for that work, we're actually also looking to see whether there's any interest, from the community, for collaborating on this, like, for enabling Magnet and also working for Kubernetes deployment. Because, with the performance improvements we have been seeing, with Magnet Yarn, it's actually pretty significant, and it would be bad, if such improvements is only limited to the Spark on Yarn deployment, but not to the Spark on Kubernetes communities. So looking forward to community collaborations on this, I guess.
I know DB's group have been working on Kubernetes quite a bit. Any other questions? I'll give another minute. Okay, here's another question. What are the group boundaries?
Yeah.
determine.
Okay, right. I was just searching through the chat history and also saw that question, right? Yeah, so let me also talk about that, the group boundaries. So this is also another topic which is discussed in detail in the paper. But I think it also helps, to discuss here as well. So the group boundary, the way to look at this is, so what's actually happening is when the Spark driver is actually starting the mapper tasks, it is actually sending one more additional information, as part of the task metadata, right? So we're actually embedding into the shuffle dependency, which is something that's already being sent from the Spark driver to all the shuffle map tasks. We're actually extending the shuffle dependency to add one more information to basically incorporate, a list of shuffle services that the Spark driver has determined that all the mapper tasks for that particular shuffle needs to work with, right? And this is one of the functionality where we're actually sort of somewhat leveraging, the existing Spark on Yarn functionalities, right? So you can sort of imagine that, so there is a sort of there is a feature, or there is a capability for the Spark drivers, to basically come up with a list of shuffle services, right? And the number of shuffle services, needed for that particular shuffle is determined by, the number of mappers and number of users for that particular shuffle, as well as the number of active Spark executors. So from there, the Spark driver will basically come up with a list of shuffle services, and they will basically send it to all the mapper tasks. So then all the mapper tasks will basically have this consistent view of that array of the shuffle service locations to work with, right? And because the mapper knows about that, for this particular shuffle, how many reducer partitions there is. So the first level of the division for group boundaries is done by first, you basically map, the sub-range of the shuffle, sort of partitions to that list of the shuffle services, right? So say for instance, if you have 100 shuffle services to work with, and your shuffle has 1,000, sort of shuffle partitions, right? So then each location will basically, sort of receive, sort of 10, sort of blocks, or so yeah, so it's responsible for 10 shuffle partitions, right? So then there's another level of, sort of a division here, because we also want to make sure that we're upper bounding, the total size of the blocks combined in each individual group. Right. So then what that means is we're going to, basically, sort of go through each one of those blocks, of course, go through the metadata, right? So we just basically adds up, individual block size until the size exceeds, a predefined threshold, and which in our case right now, we're just setting it to like 3 megabytes. And so basically once it goes over the 3 megabytes, right? So that will force the closure of a group and then starts the next group. So the purpose of that is just to make sure that, each time we're loading a group into memory, the total amount of data we need to cache into memory is actually bounded. And so this, sort of combined, sort of 2 levels of division, right? So the first level being, sort of a partition to shuffle service locations. And the second level being determined by the combined block size is what actually determines the group boundaries. Yeah.
Great question. You got another question. Please see my USEX 1999 paper on how you can do better by using fast selections.
So is this for the group boundary selection part? You can probably just reply in the QA session. Yeah, I'll definitely check out. Okay, I'll definitely check out this paper, and if you can also provide the name of the paper, that would be even great.
Great questions. Let's see. Any more questions? Okay, so if no more questions, we'll probably just thank Ming again. Thank you for a great talk and a lot of great insight for the details of Q&As. Thank you so much. Okay, that concludes our events for today.